Welcome back to the channel. In today's video, we will continue discussing pad foundation design. We discussed how to determine the dimensions and reinforcement of a pad foundation in the previous video. Today, we will carry on explaining further how to undertake a shear check for a squared foundation and column. Failure can happen either across the foundation or around the column. Punching shear is a type of failure that occurs around a column. In either case, it is only the ground force on the portion of foundation remote from the column that needs to be considered in shear calculations. This comes simply from consideration of vertical equilibrium of the free body. First, we need to check the shear across the foundation. Shear force equals ground pressure multiplied by foundation length multiplied by half the length minus half the column width minus the effective depth of the foundation. Shear area is calculated by multiplying the length by the effective depth of the foundation. As a result, shear stress equals shear force divided by shear area. Shear reinforcement is not required if the shear force is less than the value of the concrete shear stress. If the shear force is greater than the value of concrete shear stress, shear links may be provided. However, it is more common to simply increase the effective depth of foundation until the stress is less than the value of concrete shear stress, which can be obtained from the table below. The values are in terms of the percentage area of longitudinal reinforcement, and effective depth of the section D. The table assumes that cube strength of concrete is 25 newtons per square millimeters. For other values of cube strength up to a maximum of 40 newton per square millimeters. The design shear stresses can be determined by multiplying the values in the table by the factor cube root of strength of concrete divided by 25. Next, punching shear should be checked at the face of the column as well as at control perimeters within 2 effective depth from the periphery of the column. Because of the number of variables involved, it is not easy to define the distance A to the critical control perimeter. However, for hand calculations, it is regarded as sufficient to check at A equal D and 2D. The lengths of these control perimeters range from U1 to U3. Checking shear at the face of the column. Shear force equals ground pressure multiplied by the area of the foundation minus the area of the column. The shear area is equal to U3 times the effective depth. U3 is 4 times the width of the column. As a result, shear area is equal to 4 column widths multiplied by the effective depth. Shear stress is calculated by dividing shear force by shear area. Shear stress must be less than the maximum shear stress resisted by the concrete strut, which can be found in the table below with cotangent theta equals 1. Checking shear at A equals D. Shear force equals ground pressure multiplied by L squared minus 4 column width times effective depth minus pi effective depth squared. Shear area equals U2 times effective depth, which is 4 column width plus 2 pi effective depth times effective depth. Shear stress is calculated by dividing shear force by shear area. No shear reinforcement is required if shear stress is less than the concrete shear strength multiplied by 2 effective depth divided by A. Checking shear at A equals 2D. Shear force equals ground pressure times L squared minus 8 column width times effective depth minus 4 pi effective depth squared. The shear area equals U1 times the effective depth, which is 4 column width plus 4 pi effective depth times effective depth. Similarly, shear stress is calculated by dividing shear force by shear area. Again, if the shear stress is less than the concrete shear strength, no shear reinforcement is required. If these requirements are not met, then either punching shear reinforcement must be added, or preferably the depth of the pad is increased. From the previous video, the dimensions of the column are 350 mm by 350 mm, and the dimensions of the pad foundation are 2.65 meters by 2.65 meters. The ground pressure is 141 kilonewtons per square meter, 376 mm effective depth, We used a total of 10 16 mm bars. As a result, our provided steel area equals the area of a steel bar 201 mm squared, multiplied by 10, giving us 2010 mm squared. For the shear across the foundation, shear force equals the ground pressure 141, multiplied by the length of foundation 2.65, multiplied by half the length 1.325 meters, minus half the column width 0.175, minus the effective depth of the foundation 0.376. We now have a value of 289.21 kilonewtons. Then, shear area is the length 2.65 meters, multiplied by the effective depth of foundation 0.376 meters. This gives us a value of 0.9964 meters squared. As a result, shear stress equals shear force 289.21 kilonewtons, divided by shear area 0.9964 square meter, divided by 1000, to convert from kilonewton square meter to newton square millimeter. This gives us a value of 0.29 newton per square millimeter. Now, we need to compare this value with the value of concrete shear stress, which we can obtain from the table. We assume that the strength of concrete is 25 newtons per square millimeter. We need to work out reinforcement ratio, 100, times area of steel, 2010, divided by the foundation width 2650, divided by effective depth 376. This gives us a value of 0.2. By interpolation, the value of concrete shear stress equals 0.38 newton per square millimeter, which is greater than shear stress 0.29 newton millimeter squared, then no shear reinforcement is required. Next, punching shear, we will first check at the face of the column. Shear force equals ground pressure 141, multiplied by the area of the foundation 2.65 squared, minus the area of the column 0.35 squared, giving us a value of 972.9 kilonewtons. Shear area equals U2 times effective depth, where U2 equals 4 times column width. Therefore, shear area equals 4 column width 0.35 times the effective depth 0.376, which equals 0.5264. Shear stress equals shear force 972.9 kilonewton, divided by the shear area 0.5264, divided by 1000 to convert from kilonewton square meter to newton square millimeter. This gives us a value of 1.85 newton per square millimeter. As a result, maximum punishing shear resistance 4.5 newton square millimeter exceeds maximum shear stress 1.85 newton per square millimeter. Next, checking punching shear at A is equal to D. Shear force equals ground pressure 141 times L 2.65 squared minus 4 column width 0.35 times effective depth 0.376 minus pi effective depth 0.376 squared. This gives us a value of 853.4 kilonewtons. Shear area equals U2 times effective depth, which is 4 column width 0.35 plus 2 pi effective depth 0.376 times effective depth 0.376. This gives us a value of 1.414. Shear stress equals shear force divided by shear area, which is 0.6 newton per square millimeter. Shear stress 0.6 newton square millimeter is less than the concrete shear strength 0.38 newton square millimeter, multiplied by 2 effective depth, divided by A, which is 0.77 newton square millimeter. Hence, no shear reinforcement is required. Lastly, let's check the shear at A equals 2D. Shear force equals ground pressure 141 times L 2.65 squared minus 8 column width 0.35 times effective depth 0.376 minus 4 pi effective depth 0.376 squared. This results in a value of 591.4 kilonewtons. Shear area equals U1 times effective depth, which is 4 column width 0.35, plus 4 pi effective depth 0.376, times effective depth 0.376. This gives us a value of 2.3. Therefore, shear stress equals shear force, divided by shear area, which is 0.26, which is less than the concrete shear strength 0.38 Newton square millimeter. Hence, no shear reinforcement is required. Thanks for watching. We hope you found some useful tips. Check out our website at structuralengineercalcs.com. Please like and subscribe, and let us know what would you like to see next. The human footprint is a masterpiece of engineering and a work of art. Stay safe. Goodbye, and see you soon.